So in this session, I'm going to discuss the question which appeared in NET-JRF examination in June 2019. The first question is, in a system comprising of approximately 10 power 23 distinguishable particles, each particle may occupy any of the 20 distinct states. The maximum value of the entropy per particle is nearest to. So here we are going to make use of the relationship that connects the entropy with the number of microstates basically. So S, that is equal to Kb ln omega. Here omega is basically the thermodynamic probability of the system. Thermodynamic probability, or also we call this as the number of accessible microstates to the system. Accessible microstates to a system. Okay, so here we are having 10 power 23 distinguishable particles. Okay, so let's call them as n, denote by n, which is equal to 10 power 23. Okay, now we are having 20 distinct states. Okay, so because they are distinguishable particles, so let's continue with the first particle. Okay, so for the first particle we are having how many options, because we have to put the particles in out of any one of the 20 distinct states. So for the first particle to enter into any one of them, we are having 20 different possibilities. Okay, now for the second particle, okay, again because particles are distinguishable, so there is no constraint on the occupancy. Okay, so again we will have 20 distinct possibilities. Okay, similarly for the third particle we will have 20 possibility. This way we can extend this the same logic up to the nth particle. Okay, and nth particle will again, because particles are distinguishable, we will have 20 distinct possibilities. Okay, so now the total number of microstates that will be omega. That will be simply the, if you let's say we call this as omega 1, omega 2, omega 3, and let's say this is omega n. Okay, now this omega 1, it's independent of omega 2, and omega 2, it's independent of omega 3. All these are not correlated with each other. Okay, so therefore the total probability will be the product of all these quantities, omega 1, omega 2, omega 3, and so on, omega n, and that will be simply 20 power n. Okay, now by making use of the relation 1, the total probability that's given by S, that is equal to Kb ln omega, and that is equal to Kb ln 20 power n. Note that n here it is 10 power 23, because we are given a system of 10 power 23 distinguishable particles. So here this can be further rewritten as n Kb ln 20, and because we are asked in the question that the entropy per particle, so that means we can divide it by n, S by n, that is equal to Kb ln 20. And if you further evaluate the value of ln 20, this will comes out to be 2.99 Kb, and this is approximately equal to 3 Kb. So that's the value of the entropy per particle. So therefore option B is correct here. Consider a classical gas in thermal equilibrium at temperature T1 and T2, where T1 is smaller than T2. Then which of the following graphs correctly represents the qualitative behavior of the probability density function of the x component of the velocity? Okay, so first of all we should have an idea about the probability distribution function when you consider the one-dimensional motion in Maxwell-Boltzmann probability distribution. So the correct expression is given by, let's denote that P Vx, and that is equal to m upon 2 pi kt power 1 by 2 exponential minus m Vx square upon 2 kbt. Okay, where velocity may range from minus infinity to plus infinity. Okay, let's call this as our equation 1 here. Okay, now let's try to understand the qualitative behavior of the probability distribution function in one dimension. Okay, so here when Vx is, let's try to understand when Vx it approaches infinity. Okay, then in that, because this is a constant term, it's constant quantity, and it depends upon the simply mass of the gas molecule and temperature at which we are working basically. Okay, so when Vx approaches infinity, so in that case the overall behavior of this probability distribution function is determined by the exponential quantity here. Okay, so exponential minus m Vx square upon 2 kVt. Okay, so when Vx it's very large, and so this is basically 1 upon exponential very large quantity. Okay, you can say, and this will tend to 0. Okay, similarly we can take an idea about the probability distribution function when Vx it's having very large negative value. So in that case also this exponent mVx square upon 2 kVt, again it can be approximated to be 0. Okay, so that means under these two extremes the function it approaches 0. Now so that means somewhere in between, let's say the common point is when Vx is equal to 0. So what is the value of this probability distribution function? So when Vx is equal to 0, the exponent will turns out to be unity. Okay, and we will be left with only this quantity. So when Vx is equal to 0, P Vx, this is equal to m upon 2 pi kVt power 1 by 2. Okay, so now we are having a qualitative idea about the behavior of this function. So let's plot it. So here we are having Vx along positive direction and Vx along negative direction. Okay, so now as we have discussed, at Vx is equal to 0, so that means we are talking about this point. So this is 0, so we are having the value for Pvx, that is equal to m upon, so let's say it's this value. So now when Vx approaches a very large value along the positive direction, so this function will behave like this. Okay, similarly, so it will behave like this in the negative direction. Now another important point that we should note here, when we are having Bx as positive or negative value. Okay, so Bx square will turns out to be a positive number, so that means this graph will be symmetrical with respect to the Bx is equal to 0. Okay, so this maximum value, this is given by, this is equal to m upon 2 pi kBt. Okay, so this is temperature dependent, power 1 by 2. Now when suppose this is a value at temperature T1, let's say this is value, let's say, okay, at T1. Okay, and then now we have to plot the same graph for the another temperature T2, which is slightly higher than this value. Okay, so that means at Vx is equal to 0, the value at Vx is equal to 0 will be m upon 2 pi kBt. But now when T2 is slightly larger than T1, so that means for larger temperature, so the value here that will be reduced. Okay, and the function will behave like this. Okay, so we can say that this is for T1, and the second graph that we have plotted, this is for temperature T2, such that T2 is greater than T1. Now here you should also note that at high temperature, so the curve has shifted in the downward direction. So it's because of the reason that at high temperature the number of gas molecule with larger velocity, they have increased in population. Okay, so here that's why this curve is shifting in the upward direction, and also in the negative direction also. Here this curve is shifting in the upper direction, just to accommodate the larger number of gas molecule with larger velocity. Okay, and the point is that if you just integrate the probability distribution function with an appropriate limit pvx dvx, then it will come out to be equal to m upon, keep the constant terms outside, m upon 2 pi kt power 1 by 2, and then from minus infinity to infinity exponential minus m vx square upon 2 kt dvx. Okay, so here this will be basically unity. Okay, because it's the value of the integrand, this is nothing but it's exponential minus alpha x square dx. Okay, so which is equal to under root pi by alpha. Okay, so that means this will be m upon 2 pi kt, the constant term as it is, and then the value of the integral, which is 2 pi kt upon m. So these terms will cancel with each other, so that is equal to unity. So that means overall the area under the curve, it's constant. Okay, it doesn't matter at what temperature we are talking about. So that's why, because here at Vx is equal to 0, the curve shifted in the downward direction. So therefore, to accommodate the number of gas molecule having larger velocity, the curve has shifted in the upper direction at higher velocity. Okay, so therefore if we compare the options that are given to us, the option, so the lower curve correspond to temperature T2. Okay, so here, so that means not this one, so the lower curve corresponds to temperature T2. Yes, this is the correct option. C is the correct option. So this is the lower curve, and this is the curve corresponding to temperature T1, and this is corresponding to T2, such that T2 is greater than T1. So let's continue with the next question. The statement is, the equation of state of an ideal gas is PV is equal to RT. At very low temperature, the volume expansion coefficient, that is 1 by V dV by dt, at constant pressure is given by, okay, so let's try to understand. So it's given that the volume expansion coefficient at constant pressure, that's alpha P, you can denote it, that is equal to 1 by V dV by dt at constant pressure. Okay, and we are given that it's an equation, the ideal gas PV is equal to RT. Okay, so here we have to evaluate the value of dV by dt. So let's try to evaluate that quantity dV by dt by keeping pressure constant here. So from this equation we obtain dV by dt, that is equal to R upon P basically. Okay, and then after substituting the value of dV by dt here in alpha P, so it comes out to be 1 by V multiplied by R by P. So it's basically PV by R. So from this equation again, PV by R, that is equal to 1 by T. Okay, so now we are asked that at very low temperatures, that means when temperature approaches 0, the volume expansion coefficient, which is given by this relationship, okay, so that means under this condition alpha P, which is equal to 1 by T, and when temperature approaches 0, it will diverge as 1 by T. So therefore here V is the correct option. So let's continue with the next question. And the question is, the Hamiltonian of a classical nonlinear one-dimensional oscillator is given by H equal to P square by 2m plus lambda x power 4, where lambda is greater than 0, it's a constant. The specific heat of a collection of an independent such oscillator is given by. So we have to find out the correct option, and we can solve this problem by two different methods. One is the partition function based approach, and another one is the by following the equipartition theorem. Okay, so let's try to solve this problem by using the partition function approach. So for this purpose we will solve this problem first by obtaining the expression for the partition function of a single oscillator. So for single oscillator, the partition function is given by Z1, that is equal to, because it's a single oscillator in one dimension, so this is 1 by h, and then from minus infinity to infinity. This is one integral for the space coordinate and another one for the momentum coordinate. Then exponential minus beta h, where h is the energy spectrum of the oscillator, and then the position variable, and then the momentum variable. Okay, and this is further equal to, when you substitute the value of the Hamiltonian, so this is equal to 1 by h. So integral, so I am writing the common units here, the limits basically. So exponential minus beta, and then this we can write here, because we are treating it as a one dimension, so either p square by 2m or px square by 2m, that doesn't matter. Okay, p square by 2m, let's say, plus lambda by 4 x power 4, and then dx dpx. If we are using x here, so let's add px here. So now we can separate these integrals. So this is further equal to 1 by h, and then 1 by h, its common factor here, from minus infinity to infinity, and then exponential minus, so I'm bringing the second term at the first place here, minus beta lambda by 4 x power 4, and then dx, and then the integral corresponding to the momentum coordinates, exponential minus beta px square by 2m, and then dpx. Okay, so now we can write this to be equal to this z1, that is basically equal to 1 by h, and then we will call these as integral 1 and integral multiply by integral 2. Okay, so here this is the integral 1. Okay, this is the integral 1, and integral 2 can be solved directly by making use of the one of the standard result, which is, so to solve this this is integral 2. Okay, to solve the integral 2, we will make use of the result, which is minus infinity to infinity exponential minus alpha x square dx, where alpha is a constant here. So here in integral 2, we can treat beta by 2m as a constant, which is equal to alpha, and if we apply this integral, the result of this definite integral is under root pi by alpha. And if we apply this result on this integral 2, so then integral 2 turns out to be equal to I2, that is equal to 2 pi m upon beta and its power 1 by 2. Okay, so let's call this as equation 1 and this result as equation 2. Now our trouble is to find the integral 1. So let's try to evaluate integral 1. So integral 1 can be rewritten as integral 1, this is equal to minus infinity to infinity exponential minus beta lambda by 4 x power 4 dx. Okay, and this can be further rewritten as, this is equal to 2 times 0 to infinity exponential minus beta lambda by 4 x power 4 and dx. Okay, so now we have to solve this integral. So in order to solve this integral, we will make a substitution here. So let's substitute in this integral. Let beta lambda by 4 x4 that is equal to y. Okay, so this implies dy is equal to beta lambda x cube dx. So from here we can write dx in terms of other parameters. So from here dx can be rewritten as dx that is equal to dy. So we have to simply rearrange the terms in this expression. Okay, so dx that is equal to dy upon beta lambda x cube. So again from here we can find x and we can rewrite x in terms of these parameters. So after substituting the value of x here, this turns out to be equal to dy upon beta lambda multiplied by 4 by upon beta lambda power 3 by 4. And after again cancellation of the few terms, or after adjusting all the parameters, this dx it comes out to be equal to 4 by power minus 3 by 4 divided by beta lambda power 1 by 4 dy. Now we have to make this substitution in equation 3 here. So after substituting the value of dx, we obtain the integral I1 becomes I1 is equal to 2 times 0 to infinity e power minus y and then 4 by power minus 3 by 4 power minus 3 by 4 divided by beta lambda power 1 by 4 dy, and this can be further rewritten as 2 times 0 to infinity exponential minus y by power minus 3 by 4 and then remaining terms 1 by 4 power 3 by 4 and 1 by beta lambda power 1 by 4 dy. Okay, so now what we are going to do is we are going to keep the only terms which are involved in the integration, and the constant term we will keep outside the integral. And if we do that, we can further rewrite this as this is further equal to 2 into 1 by 4 power 3 by 4 multiplied by 1 by beta lambda power 1 by 4 and then the integral 0 to infinity exponential minus y and by power 1 by 4 minus 1 dy. Okay, and if you just take a look at this integral, it's a sort of gamma function and its value is gamma 1 by 4. Okay, so that means this integral turns out to be equal to, after solving solving these all constant values, so 2 divided by 4 power 3 by 4 into 1 by beta lambda power 1 by 4 and then gamma 1 by 4. Okay, so let me check what equation number we have already given. We have already given equation number 3, so let's call this as equation number 4. Okay, so now we have determined I1 and I2. So now we can substitute the value of I1 and I2 in equation 2, sorry, not equation 2 but in equation 1. Okay, so therefore the partition function turns out to be equal to the partition function z1, that was equal to, that is equation 1 basically, 1 by h multiplied by I1 into I2. So both of these two integral I1 and I2 we have evaluated. Now we have to simply substitute the value of these integrals. So 1 by h, then I1 is this one. Okay, so I1 was 1 by h multiplied by this entire expression, so that is 2 divided by 4 power 3 by 4, 1 by beta lambda power 1 by 4 gamma 1 by 4, and then the value of the integral I2, which is equal to multiply by 2 pi m upon beta power 1 by 2. Okay, so let's call this as equation 5. Now, because in the question we are asked to find out the heat capacity, and for to find out the expression for the heat capacity, we must first know the average energy for the system of this n oscillators, and we can easily determine the average energy from the partition function by making use of the relationship, which is the average energy for single oscillator, that is equal to minus curly beta of ln z. Okay, so that means we only need to worry about the terms which contain the beta parameter. So here in equation 5, so what I'm going to do is I can write this, the partition function z1, that is equal to, I'm clubbing all the terms, all the constant terms in parameter c here, and then if I just take a look at the beta parameter, so beta is here, beta power 1 by beta power 1 by 4 and 1 by beta power 1 by 2, and if we solve this, so this turns out to be equal to z1, that is equal to some constant term, and then beta power minus 3 by 4. Now our job is almost done here, so let me call this as equation 6 here. Okay, now if by making use of this definition, that is equation 7 here, which allow us to determine the average energy. Okay, so by making use of equation 6 and 7, the average energy per oscillator is given by E1, that is equal to minus curly beta of ln z. Okay, so that is equal to minus curly beta of ln c beta power minus 3 by 4. So from here we can easily determine the value of average energy, and after performing the differentiation here, so this is equal to minus 1 by c power beta, c into beta power minus 3 by 4. Okay, and then c beta power minus 3 by 4 minus 1, and then a factor of minus 3 by 4 here. Okay, and this is equal to, basically after solving this entire expression, the 3 by 4 beta power minus 1. So this is the energy per oscillator. Okay, so that means this is equal to 3 by 4 kVt. So this is for the single oscillator. So, and if we want to write the expression for the energy, the total energy for n oscillator, so that is equal to U total energy, that is equal to n multiplied by the average energy per oscillator. So therefore this is equal to 3 by 4 n kVt. So from here we can easily determine the heat capacity, that is equal to dCV, that is equal to du by dt, and constant volume, and that is equal to nothing but 3 by 4 n kb. Okay, so this is our final answer, and let's see with which option it matches. So here option V, it's the correct one here. So as I mentioned in the beginning, we can also solve this problem by making use of the equipartition theorem. But the equipartition theorem, basically it's valid for the scalar energy terms. Okay, so let me give you a hint here, so how we can solve this problem immediately within 1 minute by making use of that standard results. So equipartition theorem says that, suppose we consider a expression for the energy which is equal to, let's say, px square by 2m, and plus, let's say it's another energy term, it's basically the potential energy term for the harmonic oscillator. Okay, so here we are having two squared energy terms, and equipartition theorem says that each squared energy term, it contributes half kT. Okay, so that means this term will also contribute half kT to the total average energy of the oscillator. So then the average energy per oscillator, where we are having only the squared energy term. This is the first squared energy term and the second squared energy term. So according to this result, the average energy per oscillator will be, that's kT. But now in the expression, the energy expression that is given to us, it doesn't contain, it not only contain the square energy term, but it contain a energy term involving the fourth power of the displacement. Okay, so we are given a value of the Hamiltonian, which is p square by 2m plus lambda x4. Okay, so for this case, we can easily obtain the average energy, that is half kT, by making use of this equipartition theorem. But for the second case, which consists of a energy term having fourth power of the displacement, so in this case the average energy contribution will be kVt divided by n, where n is the index of the displacement. So here it's 4, so we should write here 4 here. Okay, so and if you just solve it, so it will come out to equal to 3 by 4 kVt. Okay, so that is for one single oscillator. So in same way, the total energy will be n multiplied by the average energy per oscillator, which is 3 by 4 kT, so 3 by 4 kVt. So then again we are at the same result again. But remember that this result we cannot use for the terms. For instance, sometimes in the question there may be a term involving x with the power 3 also, but then we cannot make use of this result directly. We have to actually follow the partition function approach in that case. So 3 by 4 n kVt, and this will result in the CV value, which is equal to 3 by 4 n kV, which is exactly identical to the results that we just obtained by making use of the partition function approach. At each time step, a random walker in one dimension either remain at the same point with probability 1 by 4. Okay, so let's draw the diagram first and then we will try to solve it. Okay, so if the random walker is staying at the same point, then the probability it's 1 by 4. Okay, or moves by a distance of lambda. So if it's moving by a distance of lambda to the right or to the left, okay, so then the probability is 3 by 8. Okay, so that means it is 3 by 8 in both cases. Okay, so after n such steps, its root mean square displacement is, so we have to find the root mean square displacement after n steps. Okay, so we can solve this problem easily. So let's try to find out the mean square displacement of the random walker. So the mean square displacement of random walker it is given by x square, and because we are having n such steps, so n and then x square I. Okay, so this is equal to n, and then because we are having three different probability values, so we will have three terms. Okay, so if the walker is at the same position, so then x will be 0 here, so 0 square and the corresponding multiply by the corresponding probability, which is 1 by 4. 0 multiplied by 1 by 4 plus x square again, so it is basically delta when it's if it's moving along the right hand side, so then x square it's delta square and multiply by the corresponding probability, so that is multiply by 3 by 8 and then plus the x square if it's moving along the left direction, so it's minus delta square, basically minus delta square and then multiply by the corresponding probability. Okay, so after evaluating it, it comes out to be equal to 3 by 4 n delta square. Okay, so therefore RMS displacement, that is x square, this is equal to delta times 3n by 4 under root, and this matches with the option C. So therefore C is the correct option here. So let's continue with the next question. The statement is, the Hamiltonian of three Ising spins S1, S2 and S3, where each spin can take value of plus minus 1, is H equal to, so we are given the Hamiltonian of the system, H, that is equal to minus J S1 S2 plus S2 S3 minus H S1, where J and H are given to be positive constants. Okay, now we have to find the mean value of S3 in equilibrium at temperature T. Okay, so the mean value of S3 can be calculated as S3. Okay, this is equal to summation I S3 exponential minus beta HI upon summation over I exponential minus beta HI. So here I have written here HI. So HI basically corresponds to various different values when we will substitute the value of S1, S2 and S3, because it's given in the statement of the question that each individual spin can take a value of plus minus 1. Okay, so that means S1, S2 and S3, they can, all of these three spins, they can take a value of plus minus 1. So we have to look for the various possibilities for these three spins. Okay, and then after determining those different HI values, after substituting these HI values, then we will be able to determine the average value of the S3. Okay, so let's try to figure out all those possible values. So for that we will make use of this Hamiltonian. Okay, so let's try to figure out those values. So here I'm going to draw a table for that purpose. Okay, the first column will contain S1 values, the second one will contain S2, and the third one will contain S3. Okay, and the last one will contain the HI values. Okay, so which will be simply calculated from the given statement of the Hamiltonian, which is equal to minus J into S1 S2 plus S2 S3 minus H multiplied by S1. So that is the Hamiltonian basically. Okay, so now here S1 and S2 and S3, they can have plus 1 or minus 1 value. So I will write here all possible values for these three spins: minus 1, plus 1, 1, minus 1, 1, 1. Okay, and there are a few more values which are feasible for all these three spin: 1, minus 1, and then minus 1, minus 1, plus 1, minus 1, 1, minus 1, and then 1, minus 1, minus 1, and then all with negative minus 1. So these are the possible options available for the three spins S1, S2 and S3. Okay, now we will calculate what is the corresponding value of HI. For instance, if we take S1, S2 and S3 all three positive, so S1, S2, that will be 1. So here we multiply 1 with 1, we will have 1 plus S2, S3. So S2 into S3, S2 is 1 and S3 is 1. That will give us 1 plus 1, so that is minus 2j. So here for the first term will be minus 2j, and then minus h multiplied by s1. So s1 is 1 here, so minus h here. Similarly, for other values of S1, S2, S3, we can calculate the energy by making use of this expression, and for the second case it is H, and for the third one it is 2J minus H, and similarly we can write for the another combinations minus H. Here we will have H and then 2J plus H minus H minus 2J plus H. Now we have determined all these energy values. Now we can calculate the corresponding value for the average value of the spin S3. Okay, so this is equal to S3. This is equal to, now okay, let me go back to the previous page. Okay, so now the first term will be S3 multiplied by corresponding exponential minus beta H1. If I call this as the first energy value, if I call this as, let me call this as H1, and this is as H2, and this is as H3, and so on. So similarly we can call other energy terms as H4, H5, H6, and so on. Okay, so if you do that, the average value of S3, so that is equal to S3, that is 1 for the first case. Okay, so this is equal to 1, then exponential minus beta H1. So exponential minus beta H1 will give us exponential beta into 2J plus H. Okay, and then the second term plus the S3, that is 1 for the second case also. Okay, so plus 1, and now we have the H. Okay, let me go back to the previous page again. So now in this case we are having two H values for energies. One is this one and another one is this one. So I'm going to club these two terms here. Similarly we are going to follow the same procedure for the remaining energy terms, and if I club these two terms, so here I will have a factor of 2 here. That means it's a degeneracy factor basically, plus 2 exponential minus beta H. Okay, and then the next term exponential minus beta 2J minus H, and then next term minus 2, again a degeneracy of 2 here, for energy equal to minus H, exponential beta H minus exponential minus beta into 2J plus H minus exponential minus beta minus 2J plus H divided by, so in the denominator we will have only the partition function basically. If you just take a look at this here, this so this is the partition function basically. So in the denominator all these terms will appear in the denominator. Okay, so this is equal to exponential beta into 2J plus H plus 2 exponential minus beta H plus exponential minus beta 2J minus H plus 2 exponential beta H. Please pay attention that here the negative sign has occurred because of the value of S3 here, for instance here as well as here. Okay, so then the next term plus exponential minus beta 2J plus H plus exponential minus beta minus 2J plus H. Now after writing this expression, we have to simply adjust all of these terms so that we arrived at a simple result here. So this can be again rewritten as exponential beta H multiplied by exponential. So we are taking exponential beta H term common from all the terms in the numerator. So inside we are left with exponential 2 beta J plus exponential minus 2 beta J minus 2 plus exponential minus beta h, and then 2 minus exponential minus 2 beta j minus exponential 2 beta j. Okay, now in the denominator, same process in the denominator also. So e power beta h e power 2 beta j plus 2 plus e power minus 2 beta j plus e power minus beta h, and then 2 plus exponential minus 2 beta j plus e power 2 beta j. Okay, and this can be further rewritten as in the most simplest way. Then we are almost close to the final result. So this is equal to e power beta h minus e power minus beta h, and then the common terms inside, so which is basically this expression. Okay, so this is equal to exponential beta j minus exponential minus beta j and its whole square divided by exponential beta h plus exponential minus beta h, and then multiply by exponential beta j plus exponential minus beta j and its whole square, and this is equal to tan hyperbolic beta h and multiply by tan hyperbolic square beta j. So this term will give us the tan hyperbolic beta j square, and this is tan hyperbolic beta h basically. Okay, so therefore if we just take a look at the options which are given to us, so here it's the B, so therefore option B is the correct one here. So let's continue with the next problem. The statement is the free energy of a magnetic system as a function of its magnetization M is given by this expression F, that is equal to 1 by 2 AM square minus 1 by 4 BM4 plus 1 by 6 M6, where A and B are positive constants. So at a fixed value of A, the critical value of V, above which the minimum of F will be at a non-zero value of magnetization is. So we have to determine the value of V, so which will satisfy the given conditions. Okay, so we can solve this problem by minimizing the given free energy expression with respect to the the parameter M, which is magnetization. Okay, so what we have to do is we have to simply minimize the given free energy expression with respect to the magnetization, and by equating this to be equal to 0, so that we obtain AM minus BM cube plus M5. So after doing the differentiation, some of the terms they will cancel and we will obtain this result. So after rearranging these terms, we can obtain the value of V in terms of A, which is equal to B equal to A plus M power 4 divided by M square. Okay, so now what we are going to do is we are going to substitute this value of V again in the given equation of the free energy. So okay, let's do that. So F will be, so that is 1 by 2 A M square minus 1 by 4 B M4. Okay, so we will substitute the value of B that we have obtained, this value. Okay, so minus 1 by 4 m4 multiplied by the value of V that we just obtained by minimizing the free energy. So A plus m4 divided by m square plus m6 by 6, and for this particular value of V the free energy will be 0. Okay, and now what we have to do is we have to simply solve this expression, and for that we can expand the terms 1 by 2 am square minus m4 by 4 multiplied by a by m square. So the first term, okay, and then the second term minus m4 by 4 multiplied by m4 by m square plus last term m6 by 6, and that should be equal to 0. And if you further solve this expression, so this will give you m square that is equal to under root 3a. Okay, so now we can find the value of B, okay, by substituting the value of m square in that expression. So V, so therefore V turns out to be equal to a plus m4 divided by m square. Substitute the value of m square that we obtained in terms of a, so then we will have the value of V in terms of a. So this is equal to a plus m square, okay, plus m square, so that means it's 3a basically. Okay, it is under root 3a, so this is 3a divided by m square, which is under root 3a. So this gives us B that is equal to 4a divided by under root 3a, or this can be rewritten as 16a upon 3. Okay, so therefore if you just take a look at the options which are given to us, the correct option is B here, 16a by 3.